the depiction of it. Now you can see this one is a 4-port network, meaning we can have like a waveguide that is modified in such a way that it has four outputs, ports nne yani. So if you have port 1 as the main source, the MW meaning the microwave source, it can come out of port 2, port 3, or port 4, or it can be reflected back on port 1. And the microwave devices, the one that are going to cover, are the one that are going to constitute the junction at the center. Let's go to the next slide. The scattering parameters. We have already said if one port is used as the input, it can have multiple outputs from the same input. So it is like the energy is going to be scattered inside the junction and distributed to the several outputs. So we want to see what characterizes those scatter, right? So we can use an example of a two-port. For a two-port network, as you will see in the next slides, if one port, Sam, can you go to the other slides? I explain as we see it. Now, this one is a two-port, meaning on the left there is the port 1, on the right there is the port 2. Now, if you apply an input in port 1 as V1, it's going to constitute a current I1 going inside the junction and is going to come out of port 2. Also, some of it may be reflected back and come out of the same port 1. All right? Now, on the other part, if you have port 2 as the input, it is going to constitute a current I2, which is going to come out of port 1, and some of it may be reflected back out port 2. So every port will have two possibilities. So for a two-port network, we'll have a combination of 4 possibilities, 2 for each port. Next slide. This is what we have just explained over there, and the traveling waves with the associated powers when scatter out of the ports, the microwave junction can be defined as the S parameters. Now, we are going to see the component of what is going to be reflected on what port and what is going to come out of what port. Next slide. Okay, scattering matrix is the matrix that characterizes or shows the relationship between the output or in a certain port having come from a certain port input. And we have seen for a 2 by 2 matrix, we have seen there are 4 combinations, meaning it is a 2 by 2 matrix, right? So a scattering matrix is the matrix that is going to show those scattering issues or the relationship between the input and the output. Okay, can we go to the next slide? Now, this is the for the two-port network. Again, on the left, we have the input. Letter A is showing the input. So letter A1 is the input in port 1, and A2 is the input at port 2. Letter B is used as to refer to the output only. So B1 is the output at port 1, and B2 is the output at port 2. Now, the scattering parameters is the scattering matrix is the one that is inside the block written S11, S12, S21, S22. Now, the way we name those scattering parameters, if you have S11, the first subscript refers to the output and the second subscript refers to the input. So S11 will be the output at port 1 having come from port 1. So port 1 is the output and also it is the input. So S11 will be characterized by the output at port 1, which is B1, and input at port 1, which is A1. So the ratio you can see over there is, if we go to S12, this one means, remember the first subscript is the output, the second is the input. S12 means it is the output at port 1 having come from port 2. So we have output at port 1, which is B1, over input at 2, which is A2, right? S21 is the output at port 2 having come from port 1, which is B2 over A1. S22 is the output at port 2, which is B2 over A2, which is the input at 2. Next slide. So for the that one is for the 2 by 2, and you can write the outputs in terms of the matrix and the inputs as B1 B2 equals to the matrix multiplied by the inputs, right? Now for other networks, say maybe this then was 2-port networks. If you have 3-port network, it is going to be a 3 by 3. If it is a 2, it is going to be 2 by 2. It is only 1 port is going to be a 1 by 1 matrix or just one number. So next. So we can look at the properties of the scattering matrix. What characterizes those matrices? What makes them unique? One of the properties is it is always a square matrix. So we have said if you have a 3-port network, it's going to be a 3 by 3. If it is 2-port network, it is 2 by 2. It is 4 by 4. That it is always a square matrix of the order, the same order as the number of ports. The second property is symmetric matrix. Symmetric matrix refers to the elements in the matrix. So if you have Sij is the same as Sji, you can interchange the subscript. The power in that, okay, from one port to another is the same as that other port to the initial port. So you change the subscript, and it's still going to be, the ratio is going to remain the same. So if you have S23, it's the same as S32. Next is the unitary matrix. Unitary matrix, before to figure out, okay, sir, the unitary matrix means if you have the scattering matrix and you multiply by its conjugate, complex conjugate, it's always going to give you by the conjugate, you are going to get always an identity matrix. Next, the other one is the sum of the products of each term of any umeenda sana sum back. Okay. The sum of the products of each term of any row or column multiplied by the complex conjugate of the corresponding terms of any other row or column is 0. Now this one is referring to the elements in the matrix, not the matrix itself. Remember the previous property we have seen, if you multiply the matrix by its conjugate, you get an identity. But in here, we are multiplying now the elements. If you multiply the elements with the complex conjugate, and then you sum, you get 0. Next, that's all about the matrix, the scattering matrix, and we're going to see how we can use them to get the properties of those dimensions. Now, we start with the first directional coupler, which is an E-plane. Some unaweza enda kwa next slide tuone the how it looks like. Now that's the E-plane T junction, and you can see it is like it is the initial waveguide that was there, rectangular waveguide. Then you add another arm vertically up or on the broader side. Now the initial waveguide that we had, which was rectangular, uh, constitute the collinear arms. That's the main arms, and this one that is added is called the side arm. And if you look at the orientation of the E field, it is pointing upwards, right? Now, if it is pointing upward, the side arm is placed in the same direction. So that's the side arm is parallel to the E field. And that constitutes the plane junction. That's how it is constructed. Now, next slide. Now, this one is the same plane T, now drawn in 2 dimensions kuonyesha vile inakuwa. So you can see port 1 and port 2 was the main waveguide we had, and then port 3 is the side arm that is added. Now, there are some properties in E-wave that we're going to look at, but before we go over there, port 1 and port 2 are the collinear, they are the main ports. So whenever you are connecting this junction, whatever, if you pick port 1 to be an input, port 2 has to be an input also, and port 3 by default will be the output. Now, that's the scattering matrix that is defined by equation 1. If we go to the other property, the scattering coefficient S13 and S23 are out of phase by 180 degrees. This one means it is S13 is the output at port 1 having come from port 3, and S23 is the output at port 2 having come from port 3. Sam, can you go to the your previous slide? What this means is if you can use port 3 as the input, the port 1 and port 2 are going to be the output. And what is going to happen is if port 3 is the input, the energy or the wave or the EM is going to be divided between port 1 and port 2. They are going to be divided equally, but there's going to be a change in phase. If port 1 is between port 1 and port 2, the output will be 180 degrees phase shift. Meaning, if the 1 is an electric field pointing upwards, at point at output port 2 will be an electric field pointing downwards, 180 degrees phase shift. So that's why we are using, now we can go to the next slide, Sam. That's why we are saying S23 is equals to negative S13, meaning it's a phase shift of 180. Another property is the port is, if the port is perfectly matched to the junction, meaning this side arm is perfectly matched with the maybe characteristics impedance of the original waveguide, we are not going to have any self-reflection. So S33, which means it is the output at port 3 having come from port 3, that is self-reflection, is going to be 0. So the term or the element S33 is going to be 0. Next. From the symmetric property, what we said, you can interchange the subscript. We can see S12 can be written as S21 or S21 can be written as S12. So those elements can be equated as equation 4 shows. Now, if we can use those properties to rewrite our original scattering matrix, we are going to have equation 5, which is only going to have some 4 unknowns, which is S11, S12, S13, and S22. Remember, S23, not S2, what? S1, S11, S12, S13, and S22. The others I've already shown that they can be equated and they can be, you can use the 180 phase shift and also the 00 for the self-reflection. So it narrows down to 4 unknowns, and you want to get the exact values of unknowns. Next slide. Now we can use the unitary property, which says if you take the scattering matrix, you multiply by the complex conjugate, you are going to get the identity matrix, and it is shown over there. So if you start multiplying the matrix, row 1, column 1, row 1, column 1 is going to give us S11 multiplied by the complex conjugate, which is S11 star, plus the S12 by its complex conjugate, then S13 by its complex conjugate, and we are going to get 1 from the identity matrix. Now, if you are multiplying a matrix by its conjugate, you can just simply take the magnitude of that matrix, and because the magnitude of a matrix or a number by its conjugate, the magnitude is the same, it's like the magnitude squared. So equation 6 is S11 squared plus the second term should not be S11, should be S12 squared, and the third one should be S13. That's the correction I have to do over there. So the equation 6 should read S11 modulus squared, modulus of S plus modulus of S12 squared plus modulus of S13 squared equals to unity. We can go to row 2, column 2. We are going to have S12 multiplied by its conjugate. Again, S22 multiplied by its conjugate and S13 by its conjugate, and we are going to get the equation 7. That's correct. Okay, next, row 3, column 3. Yes, we can take that one. That one is going to only have 2 terms because one of the term was S33 and it is equals to 0. So it's going to be like that. Then after multiplying all the rows and the columns, we can still multiply row 3, column 1 because we want to get the exact value, the exact number for those elements. So we can get equation 9 as S13 multiplied by its complex conjugate equals to 1. Now, equating equation 6 and 7, those are the first equations from row 1, column 1, row 2, column 2. And can you go to that previous slide? Yes, equation 6, you can see it over there, and we have done some correction in equation 6 and equation 7. You can see S11 will be there. S12 is going to be common in the two equations, and also S13 is going to be common. So if you subtract the two, what you are going to get is S11 from the first equation minus S22 from the second equation is equals to 0. And what that means is S11 is equals to S22. Tunaenda the next slide. And that is what equation 10 is showing, that if you subtract or you add, it's a subtraction of the two equations, we're going to get S11 is equals to S. Still, we are slowly eliminating those so many elements. Naanza kuzifanya which is giving unity, and you can see twice the magnitude of S13 squared is the one that is going to give unity. So to working out the S13, unapata ni 1 over root 2 because you have to divide by 2 and then get the square root. So up to there we have gotten the exact value of S13, which is 1 over root 2. Next. Now from equation 9, which was row 3, column 1, we had S13 multiplied by complex conjugate of S11 and also minus S13 multiplied by conjugate of S12. Factoring out S13 because it is common, we get inside the bracket S11 minus S12 equals to 0. Hapo kuna equals to 0 that is left. And because we have already gotten the value of S13 as 1 over root 2, we know S13 cannot be 0. So what is going to be 0 is what is inside the bracket. And if you equate that one to 0, you are going to get S11 is equals to S12. And remember, we had already seen from the previous equation, S11 is equals to S22. So we can say S11 equals to S12 equals to S22. Now, using the equations 10, 11, and 12, to the equations we have derived up there, we can write the equation 6 now because we have already gotten so many. equation 6 was initially S11 modular squared plus let's see equation 6 plus S1, that one I said is S12 modular squared plus S13 modular squared is equals to 1. Now let's go to where we were. So S11 we have already seen. We have seen the value of S11 is a half. Was it a half? Was it 1 over root 2? Uh, S13 is one that we have gotten as a half. Okay, so you substitute the values from the equations you have just gotten over there. You are going to get S11 as a half, exact a half, because it's, S11 from the previous was 1 over root 2. Then you square that one is going to be a half. S12, the value is equal to S11, which is also 1 over root 2. Also, if you work out, you're going to get S11 as 1 over 2. And because we have seen that those elements are related, we can write one as the other one from the equations we have done over there. If you substitute the exact values of all those elements, we are going to get the final matrix, which is written down over there as one a 3 by 3 matrix, having the first element in row 1, column 1 as 1 over 2, row 1, column 2 as 1 over 2 again, that matrix over there. And this is the characteristic matrix of E-plane T junction. Now, E-plane, next slide. Sam? Okay, so that was all about the E-plane T. And E-plane T can be used when you want to either add or subtract the plane waves, the microwaves, because we have seen if port 3 is used as the input, it's going to get the output at port 1 and port 2 with our native phase shift. So if you put port 1 and port 2 in the same phase, what you're going to get at port 3 is the subtraction of the two. If you put port 1 and port 2 as inputs with a 180 phase shift difference, port 3 is going to add the two waves and you're going to get a magnet. Now we can look at the other junction, which is the H plane T. Some end up next step one in a diagram. Now, as we had seen previously, you are adding a side arm, but in this case, now you are adding it to the side, to the narrow side, and you can see it is the E field is going to be parallel, is oriented upward, and now you are adding the one that is perpendicular to it, or in other words, the H is the H field. If you consider the H field, if the E field is oriented vertically, the H field will be oriented across the waveguide. And you can see the side arm that is added will be parallel to the H field. That's why it's called a H point. So that's the diagram. As by construction it's like we had already seen, we had a rectangular waveguide, then you add the side arm. Next. Now, now in the plane T, uh, again, the port 1 and port 2 are the collinear. Those are the main arms, and port 3 is a side arm. So again, the collinear ports always go hand in hand. If 1 is input, then 2 is input, and 3 will be output by default. If 1 and 2 are output, 3 is the input, which is okay. But what happens over here is in the plane E, we said that if port 3 is used as the input, port 1 and 2 will be the outputs, and there will be a 180 degrees phase shift. Now in H plane, there's no that 180 degrees phase shift. So what you're going to get as if you use port 3 as the input, you're going to get an output in port 1 and port 2, and they're going to be equal and in phase. Next. Let's look at the matrix of the H plenty. The properties of H plenty can be defined as, again, it's a 3 by 3 because there are 3 ports. We can write it using those subscripts, meaning, and always remember we start with the output and then we can use the symmetrical matrix Sij equals to Sgi upon remainder first, but it is just a repetition like we had already covered in the past slides. So S12 equals to S21, S23 is equals to S32, S13 equals to S31, that one. And also the side arm have to be merged to the junction so that we don't have that self-reflection. So S33, which is the output at port 3 having come from port 3, should be 0. Those reflections, we don't need them. Okay, next. So using those properties, we can do as we had done previously. We can use the unitary property, which is the matrix multiplied by its conjugate, and then remainder rack up, but this will be repetition. Maybe if you need a clarification, you can use your hand to ask a question. So it represents a multiply row 1 column 1, which is S11 by complex S11 plus S12 multiplied by the complex conjugate, which is S12 plus S13 by its complex conjugate, and you get 1 from the identity. Then we take the magnitude, we get equation 3. Next, if we take row 2, column 2, we are going to have equation 4. If we take row 3, column 3, we are going to have equation 5. And to eliminate some terms, we use, or to get the exact value of a certain element, we can use row 3, column 1, and we are going to have equation 6, and then if you work out equation 6, we are going to get equation 7, which is, you can see the term, the value of S13 is like we had in, if we had already done the first two equations, we can add them. But in this case, now you have to subtract because there is a sign change. To subtract the two, you are going to still to get S11 as equals to S22. Then from equation 6, which was row 3, column 1, you can factor out S13 because it is common, and you are going to get plus S12 equals to 0. And outside the bracket there is S13. Already we know S13 is not equals to 0. So and we can write it as equals to S negative S12, and remember it was also equals to S22. That's equation 9. Okay, we can continue. Next. Okay, that's the equation 10. Is the one that is giving the exact value of S11, having worked out these equations up there. So from equation 8, we can get the exact value of S12 as negative 1 over 2. And from equation 12, we can get S22 is equals to S1 is equals to a half. Now, if we substitute those exact values of those elements in our initial 3 by 3 matrix, we are going to end up with that matrix written over there. So that's the characteristic matrix of the H plane. And again, because that's the end of the H plane T, I can mention the importance of those couplers or connectors. They give they make the wave or the microwave follow a certain direction. Same, for example, if you have your source and you want to put that microwave to the antenna, kuna mahali kuna bends, so you have to direct that microwave through the bends up, ndio tunatumia hizo T connect. Okay, next. That's the map now that is showing the H plenty. Remember what I said about the B's are the outputs, the A's are the inputs, the matrix, the scattering matrix is what is going to dictate how the scattering is going to be inside the junction. And we have already derived that matrix and she's given as such. Next, we can look at the last, it's called the magic T or the hybrid, and it is a combination of those since we have an E arm which is parallel to the rotation of the E field, and there's going to be a side arm H arm which is going to be parallel to the H field. Again, port 1 and port 2 are while the major or the main waveguide, which is they are collinear, and what I said is they go hand in hand. But in this case, you can either use one port as the input, and the other one will not be used. But we are going to see that one now in a few minutes during the properties. Turn the next slide. That one is in the diagram yake for now in two dimensions. We are seeing the solid. Next slide. I'm trying to go so fast so that it is too fast. Now, characteristics of the AH plane T. One, if a signal is of equal phase and magnitude is sent to port 1 and port 2, then the output at port 4 is 0, and the output at port 3 will be the additive of both the ports 1 and 2. What this one means is, if you're using port 1 and port 2, because they are ports, one port will always be isolated. At one time, only 3 ports will be functional. 2 ports can be the input, and the other one could be an output, or one could be the input, the 2 could be output. But at one given time, one of the ports will be isolated. Now, if we use input and you let it go out through the E arm, the E arm always subtracts, and the H arm always adds. That's the long and the short of it all. Mm, Power is divided into the opposite in phase. That one we had already seen. E arm always out of phase. H arm in phase. The signal is fed at 3, then the power is divided between port 1 and 2 equal. Port 4, output at 4 due to 3 will be 0. That one is now illustrating what I have said. At one given time, one port is isolated, and the output at that port will be 0. Okay, the last bullet. If a signal is fed at one of the collinear ports, then the H arm will be used as the input, and the other one will be add one. This one means in this, as we had seen earlier, in H and E plane T, the collinear ports zinapelekana hand in hand, but in the magic T, one port can be used as the input, the other one can be neglected, and there's not going to be any output at that port. That is the isolated port. Okay, next. That one is the derivation of the matrix. I don't know whether we can close over there because time is but it is the same thing. Yeah, it's the same thing as we had done previously. The only change, because this one is a magic key and have four ports, is going to be characterized by a 4 by 4, but 4 by 4 matrix, and all the other properties are going to be held constant, or to apply over here. The unary, the symmetry, all those equations are going to be applied over here. So equation, okay, as we had seen the properties in the, okay, ukiangalia equation 2, as it has h plane t, s23 is equals to s13, meaning no change shift when 3 is the input and 2 and 1 are the output. Equation 3, as it has e plane t section, 4 and the input being 4, there's going to be an output at port 1 and port 2, and they are going to be 180 degrees phase shifted, which is that's why it is a negative over there. Then coming to equation 4, the E arm port and the H arm port are isolated such that they cannot have output at the same time. If one is we give the output of one is used as the input, the other one is isolated. It is zero. There's no output if you give. If 4 is used as the input, output at 3 will be 0, and if 3 is used as the input, output at 4 is going to be 0. So that one again eliminates two terms in the matrix, as S31 is equals to 0. That is equation 4. Next. From the symmetry property that one we have already seen over there, you can interchange those subscript, and it's going to deliver the same. Equation 6, what it means is there's no self-reflection. That one we already said that we don't want the input to be at the output at the same time. That is a waste of energy and power. So S33 equals to S44 and should be 0. Now, if you substitute those values and you work out as we have done previously, you are going to end up with the matrix written down over there. Next. And if we work all through, we can get the exact values of those elements. And next, to end up now the matrix as we have done. Hizo zote ni equations za kuderive na kuonyesha the exact value up to ile ya mwisho. So I think that's all iko pale, so tunaweza angalia application very fast. Naona time imeisha, but maybe if you need a clarification or something, tunaweza angalia the next class of sciences. I think we are done. Thank you. Hata maswali tunachukua next time. Thank you, Sam, for using the screen.